Uh, Welcome to the optical communications course. We have seen earlier that is various modes of a fiber, how that modes occurs. So for that purpose, we have considered the electric model, or we consider that a transverse electric field and how that pattern of that modes occurs inside a particular fiber that we have seen. So for that purpose, we have seen that there is a core, and through that core, a light is propagating. So generally, we say that light is to be reflecting from this boundary, but we have mentioned that small portion of it to be light is to be go inside the core that we have considered. Okay, so this way we have considered. So at the end, if you see that we say that we have received a electrical component. Consider this one here. So we can consider that this particular case because from this one is about your axis. So if it is a T1 mode, if it is a T1 mode means mode one. So that electric field is to be how it looks like. It is to be looks like that here. It is to be crossed one. Okay, it is to be crossed one. And if it is a T2 mode, so then in that case, this one is nothing but a core and a cladding now. In that case, here the field will be there. Likewise, I again redraw here now, no problem. Say that that is about the nature of electric field component. There is a small cross here, and this particular portion, it is just like because your field, whatever the rays is there, they are propagating through the core. So that's why this particular penetration. Okay, this is nothing but what we can say that is a cladding penetration, and because of that cladding penetration, this particular portion occurs. Okay, so that we have seen in the last lecture. Now, if supposed to be there is a mode two, so then nature of that electric field across this core will be different. Supposed to be, I say that this one is about a core, okay, here, and this one is about a axis of a core here, and this is nothing but your cladding. This one is a core and a cladding. So in that case, if it is a T2 mode, so in that case, a small portion, we say there is a penetration. Okay, we'll say that there is a penetration, small penetration there occur. Here is the peak occur for the given particular field, and then we say that this particular portion here. So means according to that, this one is nothing but the penetration, and here this one is nothing but the penetration, and the field is crossing here. Your field is crossing here. This one is one, this one is another. So for the given axis, okay, this particular field is crossing twice. So that's why that mode is called as a T2 mode. Similarly, if that field is crossing thrice, so it is called as a T3 mode. So this way, we have considered that a various modes of fiber. Mode means what? How your electric field, okay, that nature of that electric field looks like, and that nature of electric field looks like, that will provide you the how many number of modes there. Okay, and that modes are nothing but depending upon that T. Here we say T1, T2. Similarly, we have the different modes. We say that mode is equal to 1, mode is equal to 2, mode is equal to 3. Likewise, so we say that there are the TEM. So for the electric field, TEM, M stands for 1, 2, 3. We are getting the 3 mode. Likewise. But this light rays propagating through the core, through the particular fiber. And we are relating the modes with respect to a electric field component because we consider that a light wave propagation through the particular fiber. So when it is propagating through the fiber, so at the particular light rays, it has some vertical and a horizontal component. Means mode is propagation, that is propagating constant, and this one is about vertical. So along with that, we have a field component in this particular direction of propagation, and one component that is a perpendicular to the given axis. So this way we consider the propagation of a field component. That's why it is in the given direction. So always modes are periodic in nature and they are not depending upon that what will be the direction of a light. So we consider here e raised to what, j omega t minus beta z. That omega t, that is about a term when we have the time domain expression of the field, and this beta z, it provide you the what will be the propagation and in which direction your wave is propagating. So that is, this one is called as a your propagation constant. This one is called as a propagation constant. Okay, and if you see that, what do you mean by the different modes? So modes means what? They have the different frequencies. That mode, they have the different frequencies. So different frequencies, and that term we say that a different frequencies because the rays are, whatever the rays are propagating through the fiber, they have the different angles. Okay, because whatever the rays we say, it is propagating through this particular fiber, they have the different rays. Different rays means just like one ray is propagating at that particular point, this will maybe ray is reflecting from that point. This may ray, it will be reflecting from that point. Likewise. So this way we can say that they have the different specific angles they are propagating through the given particular fiber. So, so from this observer point of view, if you see that the different rays reaches at the boundaries at a different point, when it propagating toward this end, there may be a propagation delay. Because of that, there will be a different ray. But some of the rays they have the similar frequency, but only small variation in the frequencies, and they are propagating. So those rays we form the group of that particular rays, and they are propagating with a velocity, and that velocity is called as a group velocity. So generally we say a wave propagating, or your light is propagating through the guide. This is nothing but a core of a fiber in the z direction, and that rays are propagating through the guide with in a z direction. They have some velocity, and that velocity is called as a phase velocity. Why phase velocity? Because they have the constant phase. Because they have the constant phase, so that's why it has a velocity of propagation. That velocity is called as a phase velocity because with a constant phase. With a constant phase. But we consider that a light is a monochromatic one. So in that case, monochromatic light propagating through the guide, they have the constant phase. So that's why they have the phase velocity. But what happen in a practical, if you consider that light should not be a monochromatic, or light is propagating through the guide, they have the different uh, difference in the frequency there. Okay, light propagating in the guide, they have considered that a difference in a frequency. That particular difference of the frequencies are there. Those frequency are a similar. Okay, means we consider that a similar frequencies, similar frequencies where they form a group. Okay, they form a group, or you can say that a group of light rays or waves with a similar frequency or nearby, or you can say that a closely similar frequencies, they are propagating through the guide, and that group of this particular signal is form one particular packet. That is called as, we say, it is nothing but a packet formation of this one. and that packet does not travel, whatever the packet is formed, they are not travel with the particular phase velocity. But it is observed that they move in a group. Okay, whatever the packets with a similar frequency, they move in a group. So that's why that particular group has a velocity, and that velocity is called as a group velocity. Okay, that velocity is called as a group velocity. And that velocity, group velocity means it is depending upon that variation in the wavelength, and there is a small variation in the what we can say it is about a phase constant because of the similar frequency component and or slight difference in the particular frequency of that particular signal. Because these particular signals are propagating throughout, so that's why they have formed a packet, and that packet is, or you can say that they form a group, and that group is called as a packet, and they propagating with the velocity other than the phase velocity of this wave or a light, and that phase velocity is called as a group velocity. But generally, we say that a phase velocity in terms of a light, we say it is different than the whatever the light velocity. Why it is different? Because it is propagating in a that medium. So that's why we need to consider the medium constant. Okay, this particular medium constant needs to be considered so that we can calculate that what is the phase velocity. And again, we should know that what is the phase constant. And phase constant, generally we say that it is a twice pi by lambda. Okay, phase constant is twice pi by lambda. But again, it can be calculated or it can be obtained with respect to the whatever the refractive index of the material. So for a core, we consider N1 here. Suppose that core it is supposed to be N1 here. That is about a refractive index. So we can relate that this group velocity, or we can obtain the equation of the group velocity. If you solve it with respect to whatever the beta here, so we'll get that equation of a group velocity. Here we say that d omega by d beta. If we simplify it, okay, if we simplify this one with respect to the lambda here, so d lambda by d beta into d omega with respect to d lambda. So if you put that, okay, d by d lambda, if you take a common and put that value of a omega and put that value of this particular d beta, and after solving, we will get the equation in terms of what? After solving, we'll get the equation of a c by ng. Now this velocity and ng is nothing but what? A group index of this particular guide. This guide is propagating particular light. That's why we say that this one is nothing but the group index of this particular guide. Now consider a fiber, and that fiber is nothing but a core. If you see the core of a fiber, it is in the nature, that is it is in the form of a cylinder, okay, or cylindrical in nature. So we consider that a cylindrical fiber, and that fiber is in the nature of a cylinder here. So we'll say that it is about a cylindrical fiber. So to understand the cylindrical fiber, so we should know that what is the nature of the core. This one is about a core of a fiber, and this one is nothing but the cladding of a fiber. And if you see that it is nothing but that cylindrical in nature. It is about center of a core, and from the center of the core, whatever the radius of this particular core is there, throughout the given radius, if that fiber have the same refractive index, and there is the abrupt change at the boundary of a cladding. Okay, so here is the boundary of a core and cladding here, and there is the abrupt change in the refractive index. That is that particular fiber is called as a strip index fiber. So means Throughout this particular core, the refractive index of this particular core is a constant, but only at the boundary of a core and cladding, there is an abrupt change in the that refractive index. We say that N1 is the refractive index of the core and N2 is the refractive index of the cladding. Now at this particular boundary, toward up to the boundary, it is same N1. But when we change to the another, okay, in that case, that there will be abrupt change in the boundaries, the abrupt change in the refractive index. Now we consider this particular fiber, and based on that, variation in the refractive index core. So they are the types of fiber. Okay, the types of fiber. So in that case, that fiber is called as a step index fiber because here is this variation in the fiber refractive index that is called as a step. One step is there, so that's why it's called a step index fiber. Then we can say that a graded index fiber, step index fiber, and a graded index fiber. And that's these two particular fiber. If you consider the step index fiber, so there is abrupt variation in the refractive index. And if I draw again in the same fiber, so in the case of a graded index fiber, what happened? So this one is the radius. So in this particular radius, in this particular size, for this small r, the core index is a constant. It changes gradually. Okay, the refractive index will be changes gradually. And if you draw a curve, in the case of a tip index fiber, what happened? This one is a cladding, and this one is a core. Likewise. Now here, if we consider the refractive index profile, there is abrupt change in the variation in the refractive index. This one is the bottom center. But in the case of a gradient index fiber, so it is changes likewise. It slowly increases and then it is decreases here. So means gradually that refractive index of this particular core will be increases there. Okay, there is a at this particular center it is highest one, gradually it is decreases. So means there is variation in the refractive index of this particular fiber. And then based on that we say that your fiber is propagating a light, and that light we consider with respect to the transverse electric field, or we take a reference as the transverse electric field and we define the various modes of the fiber. Based on this particular modes, we say that there are the types of fiber. This one is the types of fiber. It is depending upon that refractive index of a fiber. And again, a types of fiber, if you consider the types of fiber with respect to the mode, there are the two types. One is called as a single mode fiber. According to the modes, you can say that single mode fiber and a multi-mode fiber. Okay, there are the fiber name that is called a single mode fiber and a multi-mode fiber. Now, the single mode means what? Only a single mode, only one mode is propagating through the fiber. But in the case of a multi-mode fiber, various multiple modes are propagating through the fiber. Now, based on this particular mode, so if you see the core radius or a diameter of this fiber, for a single mode fiber, that core will be a small. Okay, that size of this core will be small. And if you consider that multimode fiber, that core size is large. Small core size, large core size. Because Why small core size? Because only a single mode is propagating through the fiber. So that's why a core size will be a small. And here, multi-mode are propagating through the fiber, so that's why the core size of this particular fiber is a large there. So we will study here the various fiber. It can be a single mode fiber or a multi-mode fiber. So how many modes are propagating through the fiber? So we need to calculate. Or for a given particular fiber, how we can define the modes? Because we say single mode or a multi-mode fiber, that numerical aperture of this given particular fiber is changes here. Okay, that numerical aperture values. Because we can say that numerical aperture is a acceptance angle of the particular fiber. And that acceptance angle, it is depending upon totally on what will be the core size of this particular fiber. Or you can say that radius. You can say that a radius of the fiber. So, so that number, that whatever the modes propagating through the fiber, they are depending upon that what will be the radius of the fiber there. Or if you consider that only a multimode fiber instead of a single mode fiber, so even if that's based on this particular radius, how many number of modes are propagating through the fiber, okay, that will be depending upon the radius here. So to obtain the phenomena of that how many number of modes are propagating through the fiber, so we need to learn that how your wave is propagating through the fiber or how these rays are propagating through the fiber. So generally we define that wave equation, we say that del square E is equal to gamma square E. And this one is nothing but the propagation constant. And that we have defined with respect to the electric field. So similarly, we can define with respect to the magnetic field, but we consider here the with respect to the electric field. And then how your wave is propagating, it is depending upon that what will be the factor of a phase constant. And based on that, we can find out the what will be the wave number. So once we know the what is the phase constant of this particular wave propagating through it, and what is the difference in this particular refractive indexes, so that we will calculate that what will be the wave number here, and that is depending upon that a phase constant. And we can say this is the nothing but wave number, and this phase constant is varied along with the whatever the refractive index here. So we relate the wave equation here, and we can obtain the how your wave is propagating through the particular fiber. So if a cylindrical fiber is there, for that cylindrical, so equation for the cylindrical in terms of what will be the modes of propagation and what will be the radius of the particular propagation, so we can calculate that. So in that case, we'll write equation directly with respect to cylindrical coordinate system, and we can say that whatever the modes of propagations occur through this particular fiber, and the psi we consider is a constant of a wave, and your wave is propagating with respect to the whatever the radius we have, what will be the phase we have, and what will be the propagation of this particular fiber. So if you solve it, or if you relate with this particular psi with the Bessel function, so we can rewrite this particular equation, and using that we can define that how your wave is propagating. Now these are the three particular components of a wave, and that one component, if you see here, it is defined the radius of the cylinder. It is defining the radius of the cylinder, and this define the phase as per the cylindrical one. And if you solve this particular phase, we say that it is nothing but what? E raised to j, whatever the phase we have. So we can write here. And this is nothing but the phase integer. And this particular equations, if you relate here, instead of dou by dou t, and we say that with respect to the term, okay, so we can say that dou phi, that with respect to dou phi, okay, dou phi with for this particular equation. So that is what dou phi will be what? It is nothing but a jv here. And for this z, your wave is propagating in the z direction. Wave is propagating in the z direction. So that's why for this we say that dou z is equal to minus j beta. And if you solve this particular equation, so we can find out the eigenvalues for the core and cladding fiber, and that values are depending upon that what is the radius of the fiber. I'll just write directly here. Sorry, eigenvalues of core and cladding, and that eigenvalues for the core and cladding, that is, this is for the core here. We say u here, and that is depending upon that what will be the radius of the fiber, then your refractive index. Okay, then you can say it is a k is nothing but what? Wave number here, and phase constant beta square raised to 1 by 2. And this is for the cladding, W is equal to A, then beta square minus n square, k square, here, sorry, k square here, raised to 1 by 2. This is for the cladding here. And the field we can relate with respect to the radius. So in that case, we can find out the electric field. We relate everything with respect to electric field, so that we can say that G, that is nothing but the amplitude, and J is nothing but the Bessel function values for what? For the U and R. When we say that R is nothing but that less than 1, that is nothing but a core. And if R is greater than 1, that is nothing but the cladding here. If R is greater than the 1. And this R, this capital R, is nothing but what? It is nothing but the normalized radial constant. How you can normalize? With respect to the radius and the whatever the radius of the curve, and a factor for this radial distance. So this is nothing but a what? A normalized radial constant. And this one is nothing but what? We can say a amplitude here. And this one is nothing but what? A first Bessel function. And using that, we can find out a normalized frequency. that normalized frequency is equal to whatever the eigenvalues we are getting, that is nothing but u square w square raised to 1 by 2, and that is equal to what we can see ka n1 square minus n2 square raised to 1 by 2. That is nothing but a v. So this v, k is nothing but what? A twice pi by lambda. Okay, this v is nothing but what? K, we can write a twice pi by lambda, and that is about a is the radius of fiber, and n1 minus n1 square minus n2 square raised to 1 by 2 is nothing but the numerical aperture of a fiber. So this gives us the v number or if whatever the value of a fiber. And this u and w, these are all the parameters for the core and cladding, and we can say that these particular parameters are called as a decay phase parameter, or we can say that radial phase parameter or radial propagation constant parameter for the core or for the cladding there. So when your wave is propagating, so that wave number, whatever the wave number we say, it is depending upon that numerical aperture and the radius of this particular fiber. So means we say that for a given cylindrical fiber, whichever is the radius, we say that this one is about particular fiber, we say, or we say that this one is about our fiber and this one is about your core and cladding. Okay, in this particular case, we say that this one is a fiber. So at this particular center, okay, at this particular center, if it is about your light is propagating through the particular axis, so if there is a irregularity in the given particular fiber, and because of that irregularity, your signal get disturbed. Means we can say that a perturbation occur because of that. Why? Because of the deviation in the particular fiber axis, or we can say that variation in the core diameter. This one is about a core diameter, or there will be irregularities in the core and cladding boundaries, or at this particular interface. This one is about the interface for this core and a cladding now. That is about the irregularities at this core and cladding boundary, or there may be a variation in the refractive index constant in this particular core there. And that because of that, a propagation characteristics of the given particular fiber changes. Okay, how your light is propagating through this particular fiber, that will be changes because of that irregularities in the given particular fiber. So as I told you earlier, we have the a single mode fiber and a multi mode fiber. So this particular mode differ various modes of fiber. So we can connect it to fiber there. Okay, we can connect or we can make a joint of a fiber. But for that purpose, we should know that how your mode is to be coupled there. Let's see that a mode coupling. So as we say that for a given particular fiber, if there is a small variation in the core and cladding, so then propagation constant of this particular light rays will be changes. And due to the change in the propagation constant, all other values are changes there. Your velocity and everything is changes now. Now, for a given particular fiber, if there is a change in a propagating mode of this particular light or that rays, so then in that case, what happen? That particular mode cannot be coupled, or that particular mode variation in that light or variation in the propagation there occurs, so that particular single individual mode cannot propagate through the fiber. So what is the meaning of this? We say that a given particular fiber, your light is propagating through the axis here. That is about your axis of a fiber. And this one is nothing but a cladding now. Now your light, generally we say that light is propagating through this core. Okay, light is propagating through the core. Means that particular rays, they are propagating through the core here. If there is a change in the propagating mode of this light, okay, mode change means what? There is a change in the that whatever the light rays are there, there will be change in that particular rays. Okay. But if we consider that in that particular mode, light, that particular fiber, if it is supposed to be single mode fiber, we consider now. For a given single mode fiber, so that light is propagating or that particular ray is propagating, they are not changing any characteristics of that particular light. Which characteristics means what? Our fiber is good now, and in that case, there is no variation in the propagation, or there is no any changes in the velocity there. So in that case, there is no change in the propagation constant. But if supposed to be, because we consider that there is a fiber is a straight now, there is no variation in the fiber, it is ideal condition we consider. But if you consider that a fiber is bent now, this one is about your, instead of that, we consider that this one is about a fiber bent now. So I will draw here. If it is a straight one, there is no problem. But if that particular fiber is bent, so at this particular bend, what happen? There will be a bending loss, and due to that bending loss, so what happen? That ray, whatever it is propagating through the fiber, they, because of that bending, dispersion occur, and because of the dispersion properties, the rays are propagating through this long distance. Okay, through this particular long distance, so there may be a dispersion occur. Okay, because of that, whatever the bend. So if we consider that a coupling of this particular fiber, coupling of these modes, so in that case, it may difficult if we have the particular fiber, they are in a dispersive in a nature, or that fiber have the irregularities in the fiber, and they are in a dispersive in a nature. So because of the dispersive properties, so that modes are not able to couple. So we consider a given particular fiber. Generally, modes means what? A different light at different interactions it occurs at this particular places. If you cut the section of a particular fiber, we are getting that these are nothing but the various modes of the fiber there. So our aim is about to couple this particular light, that mode, or you can see that particular rays in a given particular fiber. That is called as a mode coupling there. So then we'll proceed further. We see that what is the exactly the various fibers and all, then again we'll come back to this particular mode coupling factor. Now consider that a step index fiber. This one is about a step index fiber. So in a step index fiber, okay, in the step index fiber, that core refractive index is a constant, as I told you earlier. Okay. Now, we say that for a given step index fiber, for the step index fiber, it has a core, and for this core, for a given particular fiber, core has a constant refractive index. It has a constant refractive index. What is the refractive index of the core? That is N1 now. Means throughout the core, that refractive index is a constant now. And that core refractive index is always higher, or you can say that high as compared to the cladding. Or you can say that a cladding has slightly, okay, cladding has a slightly low refractive index. Okay, cladding has a slightly low refractive index. So if you take a graph, or if you write this equation of a refractive index with respect to the radius of this particular fiber, so we can say that n of r is equal to what? We say n1, that is the refractive index of a core, n2 is a refractive index of a cladding, and in that case, r, when we have it is less than this particular a, not same. Okay, less than a. So in that case, we can say it is nothing but a core. If r, which is greater than or equal to a, then that material will be nothing but that particular region will be belongs to the cladding. So means for the given step index fiber, this one is about the radius of the fiber, radius of the fiber, and this one is about the cladding now. We consider that this is nothing but a r now, from the center to the cladding now. So this is nothing but a. Okay, your radius is what? It is less than the a, is nothing but a core, and throughout this particular core, that refractive index is a constant, that is about n1. Throughout the core, it will be the n1. But when that n1 is a higher, it is greater. And in a cladding, in this particular region, in the cladding, that refractive index will be a n2 here. So there is a variation in the refractive index, or you can say that a abrupt change in the refractive index in the boundary at the boundaries of the core and cladding. So for the given particular fiber, we can consider that